In the second example, we have a real-world scenario to investigate, which is always my favorite because we see why hypothesis tests are useful versus working in the abstract. So in the second example, we have the claim that the mean systolic blood pressure of all healthy adults is less than 123 mmHg. The claim is always made about an entire population. The claim is always about an unknown population parameter. So in this case, we're going to perform a hypothesis test about the mean blood pressure for all healthy adults. We're going to denote that as the Greek letter mu. We do have some sample data. For 271 healthy adults in our sample, the mean blood pressure level was 122.73, and the standard deviation for the sample was 15.03. In this scenario, we're going to perform a full hypothesis test. So even though there are 4 specific questions, I'm going to write it out complete with all of the components that I would expect you to include in your hypothesis test reporting. I like to make some notes to myself about what's given. Sample size here is 271. The sample mean, which we'll denote with X bar, was 122.73, and the sample standard deviation S was 15.03. First, I'm going to define what the unknown population parameter mu stands for. So I'm going to say, let mu represent the mean systolic blood pressure of all healthy adults measured in the appropriate units. Next, we're going to state the null and alternative hypotheses in symbolic form. Note that the original claim states that the blood pressure is less than 123. That's a statement of inequality, so that is going to be the alternative hypothesis, that mu is less than 123. The statement of equality is always the null hypothesis, so H naught will state that mu is equal to 123. Because of the direction of the alternative hypothesis, this is going to be a one-tail test. Specifically, it will be a left-tail test. Next, we're going to identify what type of test statistic will be appropriate, and then we're going to calculate it. In this case, because the population standard deviation sigma is not known, we only have the sample standard deviation. We will be using the t-distribution with 270 degrees of freedom. Recall that the degrees of freedom is always the sample size minus 1. Again, the difference between using a t-distribution versus the z-distribution is that if the population standard deviation sigma is given, then we use z. But in this case, the population standard deviation sigma is not given. Instead, we're having to use a sample standard deviation. That's what leads us to use the t-distribution. So let's go ahead and calculate t. The test statistic t has the following formula. It's the sample mean x bar minus the claimed value of the population mean mu divided by the adjusted standard deviation called the standard error, which is the sample standard deviation divided by the square root of the sample size. Sometimes I like to put parentheses around this denominator to show that this calculation must be performed first before dividing the difference by the standard error. So we have 122.73 for x bar minus 123, the claimed value of mu, in the numerator. In the denominator, we have our sample standard deviation S divided by the square root of our sample size n, and this will give us an approximate test statistic of negative 0.296. Now, let's find the critical region for this test. If we go back and look at the third question, we already answered the first. We stated the hypotheses. We already identified and calculated the test statistic. The third part was to identify the critical region. And then finally, we're going to make a decision as to whether we have enough evidence to reject H naught or not reject H naught using a significance level equal to 0.05. So alpha will be 0.05 in our case. So let's go back to looking at the critical region. You might recall from our first example, they were asking us to calculate the p-value, and we certainly could use the p-value method to answer this question. However, t-distributions are a little different in the sense that the t-distribution table does not give us precise p-values. That's why the critical region method is a little bit more straightforward. So let's go through what that looks like. First of all, here is our t-distribution. Recall that our test statistic is just to the left of the mean because it is a negative number, but it's just a little bit to the left of 0. So our test statistic is going to be just to the left of the peak of that curve. Using the t-distribution table, we want to find what t-value has an area in one tail equal to 0.05. Well, we use the t-distribution table, and there are no rows for exactly 270 degrees of freedom. So we have to use the next conservative available value, which is 200 degrees of freedom. It's best to always go down to the next available number than to round up, because you're making some assumptions about having a larger sample size than you actually have when you round up. So we're going to use 200 degrees of freedom, which is the first available row in our t-distribution table. And then across the top, we're going to find the column that has area in one tail equal to 0.05. And we see that the correct t value is negative 1.653. Here is the t-distribution table from your formula packet. Again, degrees of freedom, we'll see that there is no row for 270 degrees of freedom. So the next lowest available row would give us 200 degrees of freedom. So we're going to use this row right here. And then we're going to match that up with the correct column. We have a one-tailed test, so we're looking for area in one tail to be equal to our significance level. Our significance level was 0.05. So we're going to be using this column right here where the area in one tail is 0.05. So we see it's the second to the last column. And if we follow that column down to the row with 200 degrees of freedom, we'll see that the correct t value is 1.653. 1.653. Now, because we are working in the left tail, it makes sense that our t value would be negative. So we're going to use common sense and say that the correct t value is negative 1.653 using symmetry. All right, so here is our critical region. Our critical region is the area beyond that t value that we used by looking up the significance level of 0.05. If our test statistic fell in that critical region, we would say that we have sufficient evidence to reject the null hypothesis. However, our test statistic clearly does not fall in the critical region. Therefore, the correct conclusion is that we do not have sufficient evidence to reject H0. Therefore, we fail to reject H0. In this case, because we have a real world context, we can translate that into an understandable statement. We do not have sufficient evidence against the claim that the mean systolic blood pressure for all healthy adults is equal to 123 units. Remember, we always write our conclusion in terms of the null hypothesis, which is a statement of equality.